So this is the fourth video for Unit 9 over the ideal gas law. So before we dive into the ideal gas law, we need to go over a very important law known as Avogadro's law. Hopefully you recognize the name Avogadro's because this is the scientist that discovered how many particles are in 1 mole. And he had a number named after him, and that number was 6.02 times 10 to the 23rd. So remember, that's how many things are in 1 mole. And Avogadro's law states that equal volumes of gases at the same temperature and pressure contain the same number of molecules. So regardless of what type of gases you're comparing, if they're at equal volume, equal temperature, and pressure, they will have the same number of molecules. So I have an example that I've drawn below. I've got 3 different gases, hydrogen, oxygen, and carbon dioxide, and they contain the same number of molecules because they are at the same volume. Notice they are also at the same temperature and pressure. This is a situation that you do need to have memorized. It's known as STP, or standard temperature and pressure, which is 1 atmosphere and 0 degrees Celsius. So they have the same number of molecules in each container, and since these are gases that are at STP, they're occupying all the same volume, which is also a number that you need to memorize, which is 22.4 liters. Each of these containers, because it is at standard temperature and pressure, they have the same number of particles and also the same volume. And so 22.4 liters will represent the volume of each of these gases, regardless of the fact that they are different types of gases and they have different masses. So hopefully the fact that I brought up Avogadro's law, it brought back up the fact that moles is something that we talk about a lot in chemistry. And that is what the ideal gas law brings into account. So we're used to always talking about pressure, volume, and temperature. And so you see that each of those 3 variables is in this formula. And there are going to be 2 new variables that you haven't seen before. Obviously, the R is a number that you do not have to have memorized. It's on your reference sheet. That is the constant. And so that is always going to be the same number no matter what problem you're dealing with. So the other new variable is N, which actually stands for mole. So you think it would be an M, but we can't use an M because M stands for meters for us. So the ideal gas law basically lets us see the relationship between pressure, volume, temperature, and moles. So let's go ahead and work out an example problem. So the problem reads, what is the pressure in atmospheres exerted by a 0.5 mole sample of nitrogen gas in a 10-liter container at 298 Kelvin? So the question is wanting to know the pressure, so we're going to be looking for P. They gave us the number of moles, so that's going to represent 0.5 in our formula. They also gave us volume, which is 10 liters, so we're not going to have to convert that. And then they gave us the temperature, which is 298 Kelvin. We also do not have to convert that. So we're going to plug this into the ideal gas law formula. And I call this the PIV-NERT formula. That's how I remember the order of the variables, PIV-NERT. So P we do not know. Volume is 10 equals 0.5 times, and remember, if you forget, they didn't give me R in the problem. I don't remember what R is. Look on your reference guide, and R is 0.0821. That is a constant, and then T is 298. So if you look, our unknown P is not alone on one side of the equal sign. So we need to get him alone, and the way that we do that is we're going to get rid of the other thing that's next to it. It's being multiplied by 10, so we're going to divide it by 10, and we got to play fair and do this on both sides of the equation. So the 10 will end up going away over here, and so we will be left with P on one side of that equal sign, and then on the other side, we just need to type that into our calculator. So you would type in 0.5 times 0.0821 times 298 and divide that by 10, and you're going to get 1.22. And because this is pressure, it is in atmospheres, and luckily enough, that is what they wanted us to find in the problem, so we won't have to convert. It's as easy as that.